will be about the effect of capillary force on stresses in soil mass. Let's look at some example when we have here we have ground surface, and then we have groundwater level about 2 meters below the ground surface, 2 meters, and we deal with something silty. Let's call it sandy silt. And let's say that unit weight of this material is 20 kilonewtons per cubic meters. So soil below the ground water will have degree of saturation 100% because it all filled with water, and above the groundwater level the degree of saturation, let's say it's 0, it's a dry soil, 0%. Okay, so what can happen is in some soils there will be a capillary rise. So water on the boundary between like wet and dry soil, it will try to go up. It's because of the capillary force. So what will actually go up? And the capillary rise depends on the type of soil, as you can see in this table. So for clay it can be very high, it can be up to 20 meters. For sandy material it can be, well, 10-20 centimeters on average. For silt it will be about from 1 to 2 meters. And let's just make assumption that in our case the rise will be about 1 meter. So this is going to be 1 meter of capillary rise. So now let's see how it will affect stresses in the soil. And we're going to take point A, which is right on this boundary A. And let's say that because of the capillary rise, the degree of saturation of this capillary zone will be 50%. So what we're going to do now, we're going to find the effective stress at point A, and we're going to find it right above point A and immediately below point A. So in this case we will consider the effect of capillary rise. So first of all we'll find the normal stress, and as you know, normal stress is a unit weight of soil times the depth of the soil. So in this case to point A will be 1 meter, so it will be 1 meter times 20 kilonewton per cubic meters will give us 20 kilonewton per square meters. And to find effective stress, we need to subtract pore pressure from the total stress. So now let's find pore pressure. So if we look at point A, above point A, just right above point A, in this case there is no water, and pore pressure will be 0 because there is no water. So just immediately below point A there is some capillary force acting here on point A, and we can estimate the pore pressure that comes from this capillary rise, capillary force, using this formula where we need to know only degree of saturation, and we need to know the unit weight of water, and we need to know the capillary rise. So you'll see that the capillary rise is 1 meter and degree of saturation 50%. So we can find that pore pressure in this case due to the capillary force is going to be negative 50 times 100. So we just remove percentage times 9.81 and times the capillary rise 1 meter will approximately give us about 4.91 kilonewton per square meters. So and it's negative, so which means that it will actually contribute to the overall stability of the soil. So it's the opposite to normal regular pore pressure. So that we also call it suction. So negative pore pressure, it's called suction. And suction is pretty good because it will keep soil particles together and it will increase the strength of soil. Okay, so now let's find the effective stress right above the point A. As we already know that pore water pressure in this case is 0 because there is no water. It will be 20 minus 0. It will be 20 kilonewton per square meters. And now let's find again effective stress at point A by just right immediately below the point A. It will be same thing, total stress minus pore water pressure, but in this case pore water pressure it's negative 4.91, so that will give us approximately 24.91 kilonewton per square. You will see that the effective stress increase due to the capillary rise, and this is actually very good for the soil because it will make it stronger. Thanks for watching this video. I hope you enjoyed. Have a nice day. Bye.